Okay, shall we start? We'll do it almost like last time, except that I will go through things a bit more before. So I have a little presentation which I can skip most of. It basically is just an overview of what we talked about this morning before lunch, about the Glauber model, about the wounded nucleon model, so that you've seen before. So the tutorial as such is here at this address, and you unpack it like I've done up here. I do wget and unpack it, and inside the directory called Angantyr, you will find these files, one of which is the presentation we're looking at right now. Okay. So what you do is basically you find your the directory where you installed Pythia last week. I happen to have it right here. And there is a program called test 70 for some weird reason, I don't know why. And you copy that to the Angantyr, sorry, to the Pythia examples directory. Sorry. And you go to that directory, and you just type make test 70. And there you go. Now we're going to take a quick look at the program as such. And you will find that it's a normal Pythia main program. You have this include Pythia 8. You also have this include heavy ions.h that we need for later purposes. Number of things to control the output, and here's the main things you need to change from a normal run. We want to collide protons with lead. So beam A is protons, beam B is lead. You have a frame type 2, which is asymmetric beam. So you set the energy separately for beam A and beam B. And then there is something here, which is fit parameters. So normally when you run an Angantyr session, it will check what energy you're using. And it will then do this fitting of the fluctuations and stuff to the semi-inclusive cross sections. And here you just specify what errors you think are tolerable for those cross sections. And it's a list of total inelastic, diffractive, and so on. You don't need to set that in principle. And then you can also set the fitted parameters. There are 3 parameters that fits use in this fitting. And normally this is done automatically. But here, to speed things up, we have taken parameters that we have fit before to this energy. And we say the number of generation fitting is equal to 0. So the fitting is done using a genetic algorithm, and you specify the number of generations you want to use in that fit. Otherwise, you do Pythia init. I think in the tutorial last week, you also found the fantastic histogramming package that comes with Pythia. It's very basic, but it works. And you have one histogram for the charged particles in mid-eta rapidity, and the forward charged particles between 4 and 5. This is what we're going to measure. 10,000 events, and you have to sum the weights because, yes?
Can I put this principle means ID is this linear pattern distribution function?
This one?
Yeah.
So this is the PDG ID number for lead.
But if the
No. It uses, it emulates nuclear pattern distributions in the way that we set up the secondary absorptive events and stuff like that. So you have an emulation of that, but you use the standard PDFs for PP that you have. What else? Yes. We have, right, sum of weights. The weight, the events in Angantyr are weighted, and that is mainly because we use a sampling of the impact parameter space, which is Gaussian rather than flat, so there comes a weighting there. It's usually not a big difference in weights. So when you generate your events with Pythia next, you will get a weight, and you sum those weights, and when you fill the histograms, you fill it with the weight, and then you have to divide out the weights afterwards.
in any case, always support, it's not like in absolute.
No, it's positive weights. So what you do is you loop over the events, over the particles in the events. You look at only final state particles, and only if they're charged, and only if they're hadrons in this case. And if the eta of the particles is less than 1, then you count it as the central particle. And if it's in this region of eta between 4 and 5, you say it's forward. And after the loop, if the number of particles is larger than 0, then you fill with some weight. That's it. These histograms, which gives this wonderful ASCII output, normally you can also tweak, and that is done here. And you can send it to and build a Python script using matplotlib, and you can run it. I will show you how to do that. So that was what the program looks like. We also want to see the output of the program. So I will run it now. So you will get the normal Pythia heading like this, but then you will get a separate initialization phase with Angantyr, with a nice sword. Please note the nice sword, the Tyrfing sword here. And this is because of this fitting procedure. In this case, we haven't set any fitting. but it first lists the target values, and those we get from a parameterization, which is included in Pythia for the proton-proton cross-section at the energy we're interested in. And these are these tolerances we specify. And then after fitting, we get the resulting fit of these numbers, and the fit we didn't do now. You can see that it's fairly good. And these are the parameters. You can also in the fit get some feeling about the non-diffractive average impact parameter, which turns out to be 1.1. And then there's a lot of information spitted out from Pythia when it initializes its multi-parton interactions. But some of these you've seen before if you've run minimum bias events. Normally it's not so big. It's mainly for the diffractive excitation. And this is done twice, once for the normal minimum bias and once for these secondary absorptive processes. And so you get another initialization of those. And then it just keeps chewing along. And we will soon. If you look at what was written here, it says it should have written out a number of events, but it didn't. I don't know why it didn't do that. Something has changed. But if you look at an event, before you saw that the 0th line in the event is the process info with the total invariant mass and so on, and then comes the beam particles. Here you will see the same thing. One would be a P and the other with lead, and then the lead will have, as children, a lot of protons or neutrons that have been hit, and some kind of nucleus remnant, just bunching together all the stuff that hasn't been hit. And there's nothing special with that nucleus remnant. It has a special code or something like that. You can look at it if you're lucky. And that's it. And now I do Python test 70.py. No, that's 70plot.py. Ka-chung, and we can look at the resulting PDF file, and it's slightly better than the ASCII output we've seen before. So this is the distribution in number of charged particles in central rapidity. Looks like this. It's bad statistics, but you can increase statistics if you think it's fun. And this is the centrality measure then, number of charged particles in the forward and backward region. So far, this is things you can do like that. The first change you should do is to plot instead of the number of charged particles per wounded, instead of the first plot there, the number of charged particles, you should plot the number of charged particles per wounded nucleons. So here we have number of participants or wounded nucleons is equal to 1. And this you should change to collect info from Angantyr to instead have the number of wounded nucleons. And if you look at main113.cc in this sample directory, you should be able to figure out what to write there. And the thing is that you need to have the heavy ion info object, which is a sub-object of the Pythia info object. So that's a task. The next task is to generate instead gold-gold collisions at 200 GeV. That means you have to somehow figure out what is the PDG ID for gold. It's not difficult. And if you want, you can plot the number of participants just to see if something happens by expanding things. One thing you should remember now is, since we're now changing the beam type, that's fine. That doesn't mean you have to change anything, but you're also changing the energy from 5 TeV to 200 GeV, which means you need to refit these parameters. And that's fairly simple. You just put this either to its default value, which is 20 or whatever you want, and then you will see this fitting procedure start. And you will see if the fit looks good afterwards. Do the same for lead-lead. And you can ponder about these questions. You should consider reducing the number of events, because it takes a while to generate heavy ion events. This is also why we generated them at 200 GeV. If you would use 5 TeV as the highest LHC energy for lead-lead, it will take a while. The more particles produced, the longer it takes, basically. Now, when you've done that, or rather, if you want to go on and use rivets, then I suggest you start by going to this page, do a git clone on what we call the rivet bootstrap script. You do that and you get a subdirectory called rivet bootstrap, and you just tell it to bootstrap, given this JN, which is the same flag that you pass on to make, so that you can use more than one core when you make all the stuff that rivet needs, and it takes a while. So better to do that in the background. You also need to specify an install path. So that will take some time. Now, when that's done, you need to inform Pythia that you have a rivet installation. And you do that by configure Pythia in the Pythia main directory. So /configure with rivet and the same install path you specified here. And Pythia will find it. You will still have to say make for Pythia. It won't rebuild everything, but some things may need to be rebuilt. And then you're ready to use rivets inside of Pythia. Or rather, you will use a program which is called main93, which is one of these programs where you don't have to actually change anything in the main program, but you use configure files or command files to tell what should be done. Now, these files are also included in this Angantyr directory, so you can copy those as well. They're called atlas pled calib and .cmd, and also atlas pled run.cmd. So I'm going to show you what they look like. Because when you run heavy ions with with Rivet, you have to do a two-phase thing. The first phase, you need to do the centrality calibration, all right? So this means just measuring the centrality variable so that that can be used in other Rivet analysis as a way to do the percentiles in the analysis, if that is what the analysis does. So here you instead get all the same things as before, but we specify them in a file. So these things you recognize from before: frame time type 2, P LED, energy P, energy LED. Again, we don't have to worry about the fit parameters, so we set sigfit engine to 0 and use what we specify here. Number of events, and then just tell this main 93 program that we want to use rivets. So main run rivet on, and add an analysis, main analysis atlas p led calib. Now that is an analysis that is included in the rivet distribution. And this is basically all you need to do. Here I also specify that I want the output to go to a specific file. And then when you eventually run this thing, you say /main93, well, you have to make it first, -c for the command file, and that will be this atlas calibration file that we just copied from the Angantyr directory. And output files should be named the same. So what will happen here is that you will get an atlas ppb calib.log, which contain the output of the run, and an atlas ppb calib.yoda. So yoda is the histogram format of rivets. When you have that, you can actually ask Rivet to plot it, and what you do is you first source the rivetenv.sh to get the proper environment variables, and if you downloaded this too early, you will see that it was a C here instead of a V, but it should be rivetenv. And you call a program called rivetmikhtml, make HTML, on this Yoda file. And what you will find is something like this. If you look in rivet plots index.html, yes, it works. And you will see here, well, this you wouldn't see because that's this next step. But here, proton-led centrality calibration, and you will see how well Angantyr here reproduced the centrality variable that we will be using to make cuts afterwards. That's a SAMI-T LED, but you can also see another histogram, which is the histogramming of the impact parameter that Rivet specifies, so that Angantyr uses. Now, the idea then is to do the real run. You then need to look in the other the atlas ppb run.cmnd. It looks exactly the same as before because we're going to generate the same kind of events. The only thing that differs is we now specify another analysis, and we say sent arrow gem. So that is an option for this analysis, to use the generator calibration for the centrality. You could have written ref instead of gen, then it would use the measured values from the experiment if it's available. And you could also use send arrow imp if you want to use this impact parameter that was generated in the calibration. And the main thing here is that you need to tell Rivet about this calibration you've done, which is in this Yoda file that we just looked at, atlas ppb calib.yoda. Otherwise, you do the same thing as before. You do main93, and now with another command file, the one we're just looking at, and another output name. So that in the end, you can do rivet mcdiml atlas pled run.yoda, and you can look at the plots. So it took me 10 minutes plus to explain what to do. And now you have a bit, 1.5 hours to actually do it if you want. And I'll be here if you have questions. Yeah?
Something the random number generator started out with the initialize, which is the seed, which is the same, or can change the clock.
So any such questions, you go to the Pythia online manual, which is here. Setup run tasks, I guess, random numbers, seeds. So the default seed is something, I don't remember what it is. And you can set it, you have to first flag that you want to set it, and then you use this parameter to name the seed, and it has to be a number between 0 and 900 million for some reason. You can put it to -1, and that means you won't give a seed, that is the default seed, or you can set it to 0, then Pythia will do just check the clock and get a number from there. This is doing the clock is sometimes dangerous because if you start a lot of jobs, approximately the same. I think it only takes this seconds since 1970 or whatever it is. So there's a large probability that you actually get the same random number sequence in 2 runs. So. On my laptop, these runs takes about 5 minutes each. So increasing the statistics, you will have to wait a while.